On September 5, 1977, a Titan IIIE Centaur rocket lifted off from Cape Canaveral, carrying a machine no larger than a compact car. Its name was Voyager 1. It weighed about 590 pounds, carried a golden phonograph record of Earth's sounds, and aimed itself at the outer planets. 47 years later, that same machine is still speaking. But it now speaks from a place no human object has ever reached. Voyager 1 is over 15 billion miles from Earth, drifting through interstellar space beyond the influence of our Sun, moving at roughly 38,000 miles per hour. Every command sent to it and every whisper it sends back obeys a brutal law, the speed of light. Radio waves, the fastest signal we possess, cross that gulf in about 22.5 hours. That single number reshapes everything. When engineers in California type an instruction and press send, they are not talking to Voyager 1 as it is, they are talking to where it will be a full day later. A question asked on Monday cannot be answered before Wednesday. A round-trip conversation, command out and confirmation back, takes roughly 45 hours, nearly 2 days of silence for every exchange. Imagine repairing a device by mail, where each letter takes 22 hours to arrive, and the device is failing in real time while you wait. There is no reset button. No technician can fly out. No part can be replaced. The only tool is a stream of radio commands sent through the giant 230-foot dishes of NASA's Deep Space Network, aimed at a target smaller than a bus and fainter than almost any signal ever tracked. By the time Voyager's reply returns, it is weaker than a fraction of a billionth of a watt. And yet, again and again, when something breaks aboard this half-century-old spacecraft, a small team of engineers on Earth finds a way to reach across that impossible distance and fix it. To understand how, we first have to understand the machine itself, a computer built before the personal computer existed, running on memory, measured not in gigabytes, but in words. Voyager 1 was designed in the early 1970s, and its brain reflects that era completely. It carries 3 separate computer systems, each with a distinct job. The computer command subsystem stores and issues instructions. The attitude and articulation control subsystem keeps the spacecraft oriented, holding its antenna toward Earth. And the flight data subsystem, the FDS, gathers measurements from the instruments and packages them into signals to send home. Together, these computers command less memory than a modern greeting card that plays a tune. The FDS holds roughly 8,000 words of memory. There is no hard drive as we know it, no operating system, no touchscreen. Data was once stored on an 8-track digital tape recorder. Instructions arrive not as apps, but as sequences of binary code, timed to execute across weeks and months. This hardware predates the Apple II, predates the floppy disk in common use, predates almost everything we associate with computing. That antiquity is now the central problem. The engineers who built Voyager designed it, wired it, and wrote its software, and most of them have retired or died. Their knowledge lives in yellowed paper manuals, in fading memos, in assembly language listings printed decades ago and stored in binders and archives. When something goes wrong today, the current team cannot simply consult a database. They dig through documentation written in a programming style few people alive still fluently read. They reconstruct the logic of a system built by hands that are gone. Commanding Voyager means thinking like an engineer of 1975 in a language of that time. For a machine hardened against a radiation environment that has been slowly degrading its circuits for nearly half a century. Every solder joint, every transistor, has absorbed decades of cosmic rays. Parts fail. Memory cells die, and the spacecraft cannot tell anyone clearly when it is hurt, because the very system that reports its health is itself vulnerable. So when Voyager 1 went quiet, in a way no one expected, the team faced a machine they could barely reach, built by people they could no longer ask. In November 2023, that machine started sending back nonsense. In November 2023, the signal from Voyager 1 was still arriving on schedule. The carrier tone came through the Deep Space Network exactly as expected. The spacecraft was alive, its antenna aimed correctly, its radio transmitting faithfully across 15 billion miles. But when engineers looked at what it was actually saying, they found nonsense. The stream of data that should have carried science measurements and engineering health reports had collapsed into a single repeating pattern. Instead of the varied binary that describes plasma readings, magnetic fields, temperatures, and voltages, Voyager 1 was sending the same sequence over and over, a stuck loop of ones and zeros that meant nothing. The pattern was uniform, mechanical, and empty. It was as if a person kept speaking, but every sentence had become the identical, meaningless syllable. The team quickly narrowed the source. The Flight Data Subsystem, the FDS, is responsible for taking raw information and packaging it into telemetry frames for transmission. Something in that packaging process had failed. The FDS was no longer assembling the data properly. Whatever the instruments and sensors were reporting, that information was being scrambled before it ever left the spacecraft. This was a uniquely frightening kind of failure. Voyager was not dead, but it was mute in the way that matters most. Engineers could confirm the probe was there, could see it was still transmitting, yet they had lost the ability to read its condition. They could no longer check its temperatures, its power levels, its orientation, or the state of its aging systems. And critically, they could no longer receive any of the interstellar science that justified keeping the mission alive. To make repairs, they needed to understand what was broken. But the only diagnostic channel available was the same corrupted telemetry, now producing gibberish. They were being asked to fix a computer that could no longer tell them what was wrong with it, across a distance where every question took nearly a full day to arrive. The team would have to hunt the fault indirectly, coaxing clues from a spacecraft that had, in effect, forgotten how to describe itself. The search would push their patience, and their 2-day feedback loop, to the limit. The investigation that followed was detective work conducted across billions of miles at the speed of light, with a 2-day delay stamped on every clue. Each idea the engineers had to test became an ordeal of patience. They would craft a command, calculate exactly how the FDS should respond, send it through the deep space network, and then wait roughly 22.5 hours for it to arrive. Then, Voyager would act, and its reply would take another 22.5 hours to return. Nearly 2 full days passed between a hypothesis and any evidence for or against it. A human debugging a laptop tries 100 things an hour. This team might test one idea every 45 hours. To learn anything, they had to be clever. In March 2024, they sent a command nicknamed a poke, an instruction that prodded the FDS to run through its software sequences and report back differently than usual. When the response came, it was not the usual meaningless loop. Buried in the altered signal, engineers found a readout, a dump of the FDS memory itself. By decoding that dump and comparing it against how the software and stored data were supposed to look, they could finally see where the corruption lived. The comparison pointed to a specific region. Roughly 3% of the FDS memory was not working. A single chip, one component among the spacecraft's aging circuitry, had failed, likely struck down by the years of radiation exposure or simple decades-old wear. That damaged section held part of the software code the FDS needed to package data correctly. With that memory unavailable, the whole packaging routine broke, and the output degenerated into the repeating pattern the team had seen since November. It was a diagnosis of extraordinary precision, extracted from a machine that could barely speak, built in the 1970s, hurtling through interstellar space. But identifying the wound was only half the battle. The damaged chip could not be repaired or replaced. The code stored there was essential. The engineers now faced a stranger challenge: to rewrite a half-century-old mind and find it a new place to think. The failed memory could not be fixed and could not be replaced, but the code it held was necessary for Voyager to function. So the team devised a workaround as elegant as it was audacious. If the damaged region could no longer store the software, they would move that software somewhere else. The problem was size. No single healthy block of FDS memory was large enough to hold the entire affected code in one piece. The memory was already tightly packed. Every word accounted for in a design finalized in the 1970s, with no spare room built in for such a crisis. The engineers' answer, developed through early 2024, was to divide the affected code into smaller sections. They broke the software into pieces, small enough to fit into the scattered healthy portions of memory that remained. Then they had to adjust the rest of the FDS programming so that every reference pointed to the new locations, ensuring the relocated pieces would still execute in the correct order and communicate properly with the rest of the system. A single misplaced address could crash the process entirely. In April 2024, they began. They uploaded the first relocated segment, the code responsible for packaging engineering data, into a new home in Voyager's memory. Then came the wait. The command traveled 22.5 hours outward. Voyager received it, rearranged part of its own mind, and reassembled its telemetry using the new arrangement. Its response began the long journey back. On April 20th, 2024, the signal arrived. For the first time in 5 months, the data made sense. The repeating gibberish was gone, replaced by clean, readable engineering telemetry. The team could once again see Voyager's health, its temperatures, its systems, its status across 15 billion miles. They had reached into a computer built before the personal computer, diagnosed a dying chip, and rewritten the machine's own software while it flew through interstellar space, all through commands that took nearly a day just to arrive. Engineering data was restored. But the mission exists for science, not just survival. The instruments measuring the space between the stars were still silent. The next task was to bring the science itself back to life. By late April 2024, engineering data flowed again, but that was only half the victory. Voyager 1 carries 4 still functioning instruments, and each had fallen silent when the flight data subsystem broke. Restoring them meant a staged recovery, one careful step at a time, across a gulf where every command took 22.5 hours to arrive and every answer took another 22.5 to return. The team could not rush. They relocated more relocated code, verified checksums, and waited out the 2-day loop before committing to the next move. On May 19, 2024, engineers restored 2 of the 4 instruments to full science mode. The signals that came back were not gibberish anymore. They were measurements. By June 2024, all 4 working instruments were returning usable scientific data once more, the mission whole again after 7 months of near death. What Voyager 1 measures now is unlike anything Earth can sense from home. It sits in interstellar space, beyond the heliopause it crossed in August 2012, where the sun's bubble of solar wind gives way to the plasma of the galaxy itself. Its magnetometer tracks magnetic fields carried on interstellar winds. Its plasma wave subsystem listens to the density of charged particles between the stars, occasionally catching the faint hum of the medium itself. Its cosmic ray and charged particle detectors count the high-energy nuclei that flood the space our sun once shielded us from. This is the first spacecraft ever to send such readings from outside the heliosphere, and in June 2024 it resumed doing exactly that, 46 years after it left the launch pad. But keeping instruments alive is not the same as keeping the spacecraft aimed. A science instrument is useless if the 12-foot high-gain antenna drifts off Earth. Voyager 1 holds its orientation using small hydrazine thrusters, firing in tiny pulses to correct its attitude. And those thrusters, running since 1977, were beginning to fail in a quieter, more insidious way than any memory chip. Deep inside their fuel lines, something was slowly closing shut, narrowing the paths that fed the propellant. The next crisis would not be about data at all. It would be about whether Voyager could still point home. Voyager 1 does not steer with rockets in the dramatic sense. It nudges. To keep its antenna locked on Earth across 15 billion miles, the spacecraft fires small attitude control thrusters in brief bursts, each puff of hydrazine correcting a drift measured in fractions of a degree. Point precision is everything. If the high-gain antenna wanders even slightly off Earth, the already faint signal, arriving with less power than a fridge bulb, vanishes into noise. The whole conversation depends on aim, but the thrusters were aging in a way no software patch could fix. Each firing leaves behind trace residue, and over 47 years those residues have begun accumulating inside the propellant inlet tubes. Silicon dioxide, a byproduct of the fuel system, was slowly caking the interior of the tubes, narrowing them like plaque in an artery. Engineers estimated the openings had shrunk dramatically, roughly from a healthy diameter down to a fraction of that width. Left unchecked, the tubes would eventually clog completely, and Voyager would lose the ability to hold itself steady. The fix, decided in 2024, was to switch. Voyager 1 carries more than one set of attitude control thrusters, redundant branches designed decades ago precisely for a mission that might outlive expectations. Engineers commanded the spacecraft to change over to a different set, relieving the clogging tubes and buying time. It sounds simple. It was not. Firing up a thruster branch that had been sitting cold in interstellar space meant risking hardware whose behavior no living engineer had directly tested in years. The temperatures out there hover near absolute survival limits, and heating the wrong component at the wrong moment could crack it. Every command still crossed that 22.5-hour one-way divide. Every confirmation still cost 2 days of silence. Switching thrusters bought margin, but it did not solve the underlying arithmetic. Voyager was running out of healthy hardware to fall back on. To guard against the total loss of pointing control, the team began eyeing a set of thrusters even older, even riskier, hardware that had been switched off and written off as unusable since 2004. Reviving the dead would be the next gamble. In 2004, engineers shut down Voyager 1's primary roll thrusters. A pair of internal heaters had failed, and without them the thrusters were considered unusable, effectively dead hardware drifting toward the stars. For over 20 years, the mission relied on backup sets to handle roll, the rotation that keeps the spacecraft oriented along its line to Earth. But by 2025, with clogging threatening the thrusters still in service, the team faced a stark possibility: run out of working roll control entirely and lose the ability to keep the antenna aimed. So they went back for the dead. The plan, executed in 2025, was to revive the roll thrusters abandoned in 2004, a backup against total loss of pointing control. It meant sending commands to reawaken systems no one had fired in more than 2 decades, on a spacecraft that could not be inspected, only trusted. The danger was specific and unforgiving. To use the dormant thrusters, engineers first had to reactivate their heaters. If the thrusters fired while still too cold, the sudden thermal shock could damage them. And there was a subtler trap. The sequence risked triggering Voyager's fault protection logic, which could shut systems down or spin the antenna away from Earth, potentially breaking contact permanently. The team weighed the numbers, wrote the commands in the machine language of a 1977 design, and sent them into the dark. Then came the wait, the same brutal arithmetic that governs everything at this distance. Roughly 2 days passed before any confirmation could return, the signal crawling home at the speed of light across 15 billion miles. When the answer arrived, the thrusters had come back to life. Hardware assumed gone forever was firing again, holding Voyager steady, extending the mission's grip on survival. It was precision resurrection, achieved blind, across an impossible gulf, using instructions for a computer built nearly half a century ago. Each rescue had bought more time, but time itself was the one thing no command could restore. Deep inside the spacecraft, the power source that made all of this possible was fading, year by year, watt by watt, toward a silence that no engineer could reverse. Everything Voyager 1 does, thinking, listening, firing, transmitting, draws on a single fading source. 3 radioisotope thermoelectric generators, powered by the steady decay of plutonium-238. That decay is relentless and one-directional. The spacecraft loses roughly 4 watts of available power every year, a slow starvation no repair can reverse. To stretch the remaining budget, engineers have already switched off heaters and shut down instruments over the decades, trading capability for a few more years of life. The arithmetic is final. Sometime in the 2030s, the generators will no longer produce enough power to run even a single instrument, and eventually not enough to speak at all. That is what makes each of these rescues so strange and so moving. The memory chip fix of April 2024, the science recovery by June, the thruster switch, the 2025 revival of hardware dead since 2004, none of it stops the ending. It only postpones it. Every intervention is a decision to keep the conversation going a little longer, knowing the last word is already scheduled. And it is a conversation carried out under almost unimaginable conditions. A team on Earth writes commands from machine designed before personal computers existed, sends them across more than 15 billion miles, and waits nearly a full day for the message to arrive, then nearly a full day again for any reply, 2 days of silence for a single exchange. They speak to a spacecraft older than most of the people now saving it, using manuals archived on paper, decoding the intentions of engineers long retired or gone. Voyager 1 will not come home. It will drift on into the galaxy for millions of years after its voice finally fades, carrying its golden record past stars no human will ever visit. But for now, it still answers. Somewhere in interstellar space, a 1977 machine hears us, obeys us, and reports back, faithfully, faintly, across the dark. When the last signal finally arrives and no more follow, we will remember what this was. Not just a mission, not just a rescue, but the farthest conversation humanity ever held.